We studied Routh-Hurwitz table and how to determine stability of a system using Routh-Hurwitz. We also studied how to determine stability of a feedback system using Routh-Hurwitz. Now we want to study special cases. Special cases in Routh-Hurwitz method are very important, and later we are going to see how they help us find out many characteristics of systems. Looking at Routh-Hurwitz table, we can see that to populate each row, we need the two rows above that specific row, and that is important. But look at how we do that. We always seem to be, let me go back, we always seem to be dividing by the same number. So here, when I want to find bn minus 1, bn minus 3, bn minus 5, I look at the first two rows, but when I do the multiplication, I always seem to end up dividing by an minus 1. See, look at here, look at here. The same for the next row. If I want to find cn minus 1, cn minus 3, cn minus 5, I seem to always end up dividing by this bn minus 1. So that creates a possibility of problems, isn't it? What if any of these first elements happens to be 0? More importantly, what if an entire row is 0, not just the first element? So these are the two special cases. So what if it is 0? How would we compute the next row? And what if all elements of a row are 0? What can we do about that? These are the two special cases. So if any of these cases happen, what we can certainly say is that our system definitely is not stable. Either it's unstable or it's marginally stable. Okay, now let's look at special case number 1. Special case number 1 is when only one element, which is the first element, is 0. So only the element in the first column is 0, but the rest of that row are not 0. So if this special case happens, we certainly have a pole on the right hand side. We certainly have an unstable system. But if we want to learn more about our system, what we can do is to substitute that 0 with a small positive number epsilon, and then continue. Let's see this example. It's easier to explain it on a numerical example. So I have the system. What's the first row? It's going to be 1, 2, 11. What's the second row? 2, 4, 10. 1, 2, 11, 2, 4, 10. So then we derive the elements of the next row. We end up having 2 times 2, subtract from it 4 times 1, divide by 2, that is a 0. And then I have 2 times 11, subtract from it 10 times 1, divide by 2, which is 6. So I have special case 1 because I have one element, the first element, that is 0. To be able to continue, I already know I have instability, but in order to continue, I substitute that 0 with an epsilon, and I say, well, epsilon is a very, very small positive number. Then I continue, so I multiply epsilon by 4, and then subtract 6 times 2 from it, and then divide by epsilon. So now I continue and populate the table, but now instead of having numbers, I end up having epsilons. It's going to be kind of ugly and messy, but I'm going to end up having a lot of epsilons everywhere. Now, after I finished my table, now I can analyze this table with remembering that epsilon is a really small positive number. So after I finished populating the table, now I look at it. Well, this is a positive number. It's very small, but it's positive. How about here? 4 epsilon minus 12, but epsilon is a very small number. So it's kind of like negative 12 divided by a positive number. So this is a negative number. And I do the analysis like that. So here, what I get in this example is that I have 1, 2 sign changes. So I have 2 poles on the right hand side. And I have instability. Okay, so that was special case 1. Special case 2 is when an entire row is 0. This is a very important case. You will later see how in root locus it helps you. So come back here later and read this slide again. So the meaning of it when you have special case 2, so if you encounter an entire row of 0, the meaning of it is that there are poles that are symmetrically located about the origin. What? I said there are poles that are symmetrically located about the origin. So I'm trying to find out how many poles are on the right hand side. That's what Routh-Hurwitz is supposed to tell me. But this is a special case. In this special case, it's telling me, hey, I can sense symmetricity. Well, symmetricity doesn't mean necessarily that I have unstable poles. It means that I have symmetricity about the origin. So the next step would be when I have this special case, we need to form something called an auxiliary polynomial, which is made by the coefficients of it. So basically, coefficients of it come from the row immediately above the row of all zeros. Then I try to solve this equation, and the poles that the equation gives me are symmetric poles. Okay, so I'm going to come back to this slide, but let's see numerical examples. We are going to come back to this slide. So I have these 3 examples. Discuss stability of the following characteristic equations. So let's look at Q1. Q1 is s cubed plus 2s squared plus 4s plus 8. So when I make the table, I'm going to have, in the first row, I'm going to have 1, 4. In the second row, I'm going to have 2, 8. Right? So then 2 times 4 minus 8 times 1 divided by 2 is 0. And the second element is going to be 0 because I have a bunch of zeros here. I have a nothing here. So now I have an entire row of zeros. Now what that means is that I know I have symmetricity among the poles. What should I do? Well, I need to form an auxiliary polynomial by going to the row right before or right above the row of all zeros. So I come to this row and I form my auxiliary polynomial by using these numbers as the coefficients of my polynomial. So what would be a polynomial with 2 and 8 as the coefficients? Well, it's gonna, and so this is s squared row. So I'm gonna have 2s squared plus 8, right? So 2s squared plus 8, put that equal to 0 and solve the auxiliary polynomial. If I have 2s squared plus 8 equal to 0, it means that I have s squared plus 4 equals to 0, or s is plus minus j2. So I found my symmetric poles. I have 2 symmetric poles, and they're on positive and negative j2. So this system does not have poles on the right hand side. These symmetric poles are not on the right hand side. And I don't have instability. So let me go back. So I found out from here, so the information from here and later are all given to me by these 2 poles. It's telling me that these 2 poles that I'm supposed to find after this row are both are on the j omega axis. For non-symmetric poles, all of their information are gonna be in the rows before this. Did I have any sign changes? No, I didn't have any sign changes. So I don't know exactly about what these poles are, which are non-symmetric, but the non-symmetric poles have shown all of their effects before they get to here. So because I have no sign changes, the non-symmetric poles are all negative, are on the left-hand side, and my symmetric poles are on the j omega axis. So I have a marginally stable system. That was this. Now how about Q2? Well, for Q2, if you do the math, I'm going to have this situation. So the auxiliary polynomial is the row above the row of all zeros. I'm going to have negative 2 square, s squared, negative 8 equals to 0. Again, I'm going to have s equals to plus minus j2. The same exact values I found before are again the symmetric poles. But look at here, I had sign change. Because I have a sign change, the non-symmetric poles seem to be on the right hand side. So look at the first column of the table. Since we have sign changes, we realize that we have one pole with positive real part, which means that the system is unstable. So this was marginally stable, this is unstable. How about the third one? Well, the first row of it would be 1, negative 4. The second row would be 3, negative 12. Again, I'm going to have a row of all zeros. Again, I go and write the auxiliary equation using these numbers as the coefficient, and I end up having s equals to positive negative 2. So now I don't have any sign changes here, so the non-symmetric poles seem to be on the left-hand side. But look at my symmetric poles. The symmetric poles are not on the imaginary axis anymore. My symmetric poles are at negative and positive 2. So one of them happens to be on the right-hand side. So one of the symmetric poles is unstable now. Right, so let's go back now to here. So the analysis. Non-symmetric poles of the system show up before the row of all zeros. Essentially, this method breaks the polynomial into a symmetric and a non-symmetric part. And everything after the row of zeros is due to symmetric poles. Everything before the row of zeros is about non-symmetric poles. And finally, when the special case happens, you either have a marginally stable system or you have an unstable system. You do not have a stable system.